Let's take a look at some differential equations here. So differential equations just means they have derivatives in them. So we're going to be looking at derivatives. And this is the last section here. This is going to be awesome. So here is a differential equation. I've got the derivative. Remember that dy dx is just like a y prime or an f prime. We have the derivative. Same old, same old. We're going to try to find what is the original function. Check this out, though. It's kind of like implicit. We have x and y over here. I say implicit? How about implicit? It's like implicit differentiation backwards. So we've got the x and the y over here. Can we find the antiderivative? We're going to learn a pretty cool technique here called separating the variables. So how do you do that? Well, we're going to split up this dy dx. We're going to get all our y's on one side and all our x's on the other. So I want to get my y's together, so I'm going to times this side by y. Whatever you do one side, you got to do the other. So we got dy dx. And then here's kind of the weird part. I can split up my derivative here. I'm going to times this side by the dx dx. So they're gone. So I'm looking at this y dy x squared dx. And what's cool about this is now we can integrate. So on this side, I'm integrating with respect to y. And then on the other side, I'm integrating with respect to x. Boom, there it is. So let's go ahead and do that. What's going to happen when I take the antiderivative of this? I'm just going to bump it up 1 to y squared, divide by that number. And you do introduce some constant we don't know. And then I'm going to do the same thing over here and bump it up 1, divide by that number. And I get a constant. You could call this C2, I guess. If this is C1, I get another constant over here. So I'm adding that constant in there. So now what I'm trying to do is I want to find what is y. You know, I have y prime, what is y? So I got to get y by itself. So what's going to happen here? Well, first thing I would probably do is subtract this constant. But what happens when you subtract constant 2 from constant 1? Do you get constant 3? I don't know. You get another constant. So really we didn't have to do all that. It's still going to be a constant. So we kind of got to wrap our brain around this idea of that it's just a constant. So C2 minus C1 is still just some constant. I call it C3 if you want. That makes you happy. But usually we don't even write that C. We just put it over on the right side because when you subtract them, you get another constant over here. Let's just finish this bad boy out. Times both sides by 2. So you get y squared equals 2/3 x cubed. And again, you could write 2c, but there's no reason to write 2 times a constant. It is still a constant. And then the finale, what do we got to do? We got to square root both sides. So I'm looking at my y, the equation would have been the square root, and it is plus or minus, I don't know which one, 2/3 x cubed plus c. And that c is under there. I got kind of lazy on that. Sorry about that. My B. So there is the original function. So I just solved that differential equation. I did something called separating the variables. So we're going to do a lot of separating here, and that's the antiderivative. Pretty awesome, huh? Let's try it again. So let's just do another one. So what you'll quickly probably notice that these are always going to be some kind of multiplication or division. It doesn't really work with addition or subtraction because look at this first step. The first thing I got to do over here is divide both sides by y squared. So I got to get my y's over here. So I'm looking at y squared dy. Bring the dx over. It's sine x dx. So you can probably do that in one step once you do enough of these. Then we're looking at what is the integral of y to the negative 2 with respect to y over the integral. I put a little trig function over here, kind of mix it up. It's kind of nice. So yeah, let's just go ahead and solve these. So take the antiderivative, bump it up 1, divide by that negative, divide by -1. I'm not going to put the plus c here because I'm just going to take it over here and do it over here. So what's the antiderivative of sine? I think it's negative cosine, yeah? Make sure you got the negative in front. And now there's the plus c. So you can put it over here and move it, but whatever, you're going to get a constant. I'm kind of lazy, so I'm just going to put it over there. So now once you have this, remember our whole goal is to solve this is find the antiderivative, find the original function. This is the derivative. So this looks weird. This is a really weird one. This is like -1 over y equals negative cosine plus c. So I'm trying to solve for y. So the first thing I would do is times both sides by -1. Well, when you do that, this will become positive 1 over y, and that becomes plus cosine minus a constant. But again, that constant could already be negative. Who knows? We can just put plus c. Love that constant. And then now the last thing here is the easiest way I think about these. You can multiply both sides by y and divide is the long way, but I just get in the habit of I'm just going to flip it. So 1 over y, you know, this whole thing is over 1. You can flip that over. You can flip as long as you flip this side over. So as long as you flip them both over, you are good to go. If you don't like that, or if you think I'm lying to you, don't hate. I don't know why you're hating. if you got this, you could do all the steps here. You could say, okay, really, we should times both sides by y, and they cancel. And then what do you get? You get 1 equals this whole cosine x plus c equals y. So now what are you going to do? You're going to divide both sides by cosine x plus c. So there it is. I mean, you can show all those steps and do all that, but it's especially because we're going to get more complicated. When you get 1 over y, just put him over a fraction, flip them both, and you're good to go. Fantastic. We're cruising. I thought this was going to be a long video. Let's see. Oh, okay. We got to step it up here. So now this has been generic. We've been finding, plus c generic antiderivatives. Now I want to solve for y with the initial value. I'm going to give you something from the original function. I'm going to give you some points. So now we can actually evaluate it and tell me the equation. So this is pretty cool. So if I have my derivative, I'm going to clean this up a little bit here. So let's go ahead and square them both. And again, to get this bad boy going, I need y and y's over there. So I'm going to divide by y squared. So it's 1 over y squared, and they cancel. So I've got 1 over y squared dy. Bring that dx over here. And it looks like this. Now let's integrate here. So I've got y to the -2 dy equals the integral of this. Fantastic. So it's the same thing we had just been doing. Let's go ahead and finish this. I'm going to bump it up 1. Oh, I got the same kind of issue here, don't I? To -1, divide by that -1. This will turn into x cubed, and then divide by that 3, so you get a 1/3, and plus the c. So here's what I like to do. As soon as I get that plus c, I'm not going to solve it for y. I'm actually going to plug those numbers in. It just seems way easier if you can do it right off the bat. If I do anything, maybe I'll just rewrite this as -1 over y, just so it looks a little nicer here. But don't go ahead and solve for y. I mean, you can, but you end up kind of giving yourself more work. So if I plug in 1 and 1, they're both 1. So if y is 1, it's -1 over 1. That's cool. And then the x value is also 1 cubed. So what is my c value here? I'm looking at -1 equals 1/3 plus c. So if I solve that, subtract your 1/3, subtract 1/3, I'm looking at -1 1/3, -4/3. So then I go back to where I was here. So this was my generic, and maybe this one's, let's just continue that area. This one's a little bit nicer. I go back to this, this equation I had with the plus c, and then I plug the c in there. So, we didn't know where the plus c is, like where is that antiderivative at, but now I know. This is the particular solution. I knew the initial value. This is the real for real answer here, not just one of the possibilities of answers. So again, that's what I was talking about, how let's get rid of that negative, but we got this 1 over y. It's going to flip the signs over here when you divide by the negative. And now this is what I was talking about. This is the old flippity here. Flip this side, you get y. Flip this side, you get 1 over -1/3 x cubed plus 4/3. I'm probably pretty cool with that. I know fractions and fractions aren't the most ideal, but whatevs. I think that's pretty cool to get your point across. You could, I guess, get a common denominator, clean it up if you wanted to, but I'm totally down with that. So as soon as you get that c, I go ahead and solve for it instead of solving for y. Then you can go back and solve for y because we know what c is. That's it. All right, so let's kind of bring this all together here. So if I have another differential equation here, remember this goes back to like the first section on slope fields. We can create a slope field of what is the derivative at every single point. Find the derivative of every point. You can do that by hand if you want, or I got it done. Look at that. It is all done right there for you. If you want to pause it and sketch mine. So I went ahead and drew the slope field for this thing. That was part A. This is kind of review stuff here. Write the equation of the line tangent. So boom, as soon as you see line tangent, you're thinking first derivative. Well, there's the first derivative right there. There's your dy dx. So we're golden there. And I know the point is 2 and 1. So you can just plug that in. So this is kind of review stuff. So what's the derivative? It's 4. Once you have this, at this point, that's the slope of the tangent line. You can just make an equation out of it. So it's y minus the 1 equals 4x minus 2. So that's old school. We've done that before. I just kind of want to call your attention to it again because now we're going to have the next level. And this tends to be a lot of like a total free response question on the AP exam. You got the slope field, you've got the line tangent, and then I want to know the particular solution. So this is kind of a crazy looking slope field. I want to know the one that actually goes through the point 2, 1. So the point 2, 1 is right here. So I'm actually concerned about, okay, what is the equation line that goes through there? So it's kind of some craziness going on here. If you take a look at this, and even trying to draw this thing is going to be pretty rough in there to get the general shape. But let's go ahead and find find that solution. So it's the same thing we were doing. How are we going to do that? Well, we're going to solve this differential by separating the variables. So to separate the variables, I've got y equals times dy equals 2x dx. So first thing, separate them. The next thing, integrate them. So if we integrate this, it's the integral of y and the integral of 2x dx. So let's actually go ahead and take the antiderivative here. So this becomes y squared, bump it up 1, divide by that number. Bump this bad boy up 1 to 2, divide by that, it cancels out, and you've got a plus c right here. So that's generic. That would be the generic antiderivative there, but we want the particular one at this moment in time. So as soon as I have c, I go ahead and find out what that c is. So right here, I'm going to plug in 2 and 1 just to figure out what that bad boy is. So y is 1, x is 2. Can we solve for c? Sure, 1/2 of 1 is 1/2. And that's 4 plus c. So what is c going to be? C is going to be, subtract that, minus 3.5. So c is going to be a negative 3.5. You can write as a fraction if you want. Either way is coolio. So that's it. But is that the particular solution? No. Remember, I got to plug c back in here. So I'm going to rewrite it down here so we have plenty of space. So we had 1/2 y squared equals this x squared minus 3/2 right here. So now I'm going to solve it for y. So solve this for y. I'm going to start off by multiplying both sides of the equation by 2. So they cancel. So I'm looking at y squared equals 2x squared minus 7. So that's nice. And then what do I do here? I'm going to square root both sides. And when I introduce the square root, it's this plus or minus. So it's 2x squared minus 7. So careful on this bad boy here. So now when I have this plus or minus, it's one of these. It can't be both the plus and the minus. So because that wouldn't be a function, if we, when this plus or minus these square roots, you end up getting these sideways parabolas. They don't pass the vertical line test, blah, 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 blah. So I've decided, hey, am I talking about when it's going through this point, am I talking about the plus or the minus? In this case, what am I talking about? Definitely talking about the plus. So I don't need that minus. In fact, it's wrong if you put it there. This particular solution is y equals the positive. You could write the plus, I guess, if you just want to make sure. 2x squared minus 7. That is the particular solution. If it would have been 2 negative 1 down here, totally different equation, then yes, you do need the negative in there. So the particular solution, if you want to graph it, is going to look something crazy. It's probably going to, it looks like it's this coming down slope right here, and then it's probably going to disappear. It can't be 0. There's no way it's going to be 0. So it's a piece here. If I drew the negative, it would be, oh, we don't want that. What is that? If I drew the negative, it would be the part down here, but I don't want the negative. So you have to choose when it's plus or minus. So that's kind of tricky. If it's generic, who cares? You put the plus or minus, but when it's particular, if it's positive, you got to put the plus.